Hello, everyone. Hope you guys had a good weekend. Today, we're going to be continuing the light discussion, and we're going to focus on three interactions that light has with day to day objects. Okay. If you remember from the electromagnetic unit, we said that light can behave as both a wave or a particle. Okay. It is the particle behavior of the light that allows it to do these three things. And these things are reflection, refraction, and dispersion. Dispersion, they don't have it in the word here, but dispersion. Okay. Dispersion is the third thing that we'll be talking about. Okay. Reflection is, I'm sure you guys are all aware, is just when light bounces off of a surface and provides you with a perfect image. Okay. So think of a mirror. What's going on in a mirror is that light is bouncing off of the mirror surface and going back into your eye and giving you whatever image is in front of the mirror. The reason that happens is because the mirror is a perfectly smooth surface. Okay. It has to be perfectly smooth in order for that to work. Other places you may see a reflection is in water. Okay, if you see here, you see the image of the mountain being reflected in the water. Okay, so when light hits something, the light bounces off of it. That's why you can see it. Okay, so whatever you see, in order for you to be able to see something at all, light has to hit it, that light has to bounce, and that light has to then hit your eye. So everything reflects light in some way, shape, or form. If no light is reflected, then it just looks black. Okay, and it's just looks like a void. That and you turn off all the lights in a room, everything looks black because there's no light bouncing off of anything, so you don't get an image. So that's reflection. Okay, reflection is the most obvious one here out of the three. Now, refraction is the bending of light when it transitions into a new medium. Okay. When I say the word medium, what I mean is the thing it is traveling through. Okay. So normally, us walking around, light is traveling through air. But light can also travel through water. It can travel through oil. It can travel through a bunch of things. Okay. So a medium is the thing that it is traveling through. But when light transitions from one medium to another, you get this thing called refraction. Okay, what that does is it bends the light. Okay, if you guys have ever put a straw in a liquid, which I'm sure you guys have done before, and looked at it carefully, you can see that it looks like the straw is being cut in half and like shifted, the part of it that's under the water. Okay, what you see here is you have three images. You have a stick in just a glass with no water in it. Then you have a stick with water inside it this time, and then they what they do is they put both images on top of each other, and you can see that the image where it's just air and the image where it's just water, they don't overlap, which means something is happening to the light, and what's happening is it's getting bent. Okay, so when light strikes water, some of it gets reflected. Okay, some of it gets reflected, and that's what they're showing here, but not all of it gets reflected. Okay. Some of it travels into the water. That's why you can see inside of water. Okay. So you get a partial reflection, which is why you see images on top of the water, but you can also see inside of the water. Okay. That's because some of the light goes in, but it gets bent. So the image gets distorted. Okay. So the angle, notice if I was to draw a dotted line or if I was to continue the line, it should be traveling over here, but that's not what happens. It gets refracted and it comes down a little sharper. Okay. It comes down a little sharper. And what they have on this side is that, let's say the light was coming from the water. And so you're under the water, you have a flashlight under the water. Okay. So if you were to turn on a flashlight under the water, again, some of it would get bounced back into the water, but some of it would go out of the water and into the air. And the same thing would happen. You're still going through a transition, but now it's going from water to air instead of from air to water. But as you can see, you get a refraction. They call this the refracted ray, and the light is getting bent. So if you're under the water and you're looking up, what you see isn't exactly reality, if that makes sense. Like everything is shifted a bit. So when you stick your head out of the water, things aren't going to be where you thought they were. Okay, like the image gets distorted, so that's why you have to be careful with that. You have to take that into consideration, and you can calculate this value. So how much it's going to bend, how sharp it's going to bend, that is based off of the index of refraction. Okay, the index of refraction, and that's labeled as n. That's what you're going to see here. So see, they have it labeled as n. So n is equal to c. The c, where c is the speed of light in a vacuum, and if you remember, that value is 3 times 10 to the 8 meters per second. Okay, so n is equal to c divided by the velocity in that new medium, whatever that medium may be. Okay, so if it's in water, v would be the velocity of light inside of water. Okay, but obviously to calculate that, we'd have to know what the velocity is inside of the water, but most people wouldn't know that off the top of their head. But thankfully, scientists have already done that for us. So we already have a table for it. Okay, what this is just showing you is how they develop the equation. After you plug everything in, all the different equations, this is what you end up with. Okay, this is what you end up with. So what this equation is telling you is that the index of refraction of whatever you're looking for is equal to the wavelength coming in divided by the wavelength that we know already. So let me see if I can make that a little clear. So let's say we wanted to find the index of refraction of water. Okay, let's do water again. We would have to know what it is in air and what it becomes when it enters water again. So this equation as is isn't the most useful. How we're going to be using it is we're going to be finding the wavelengths in new mediums, okay, or in different mediums. Because again, we would have to know what these wavelengths are, but we might not know that. But again, all experiments have already been done. So how we're going to be using this equation is that we're going to say that the wavelength, okay, which is the upside down y, or I believe it's gamma in the Greek letter, it's this over this, okay? So this is how we're going to be using the equation. Oops, no, wrong. This should be the blank one, and this should be that. So what this equation says is that the wavelength in the new medium, okay, so this is for the new medium, the one we don't know, okay? This is for the one we don't know. The wavelength in a new medium is equal to the wavelength in the other medium, the one it's coming from. So let me give you an example. Okay, let's say we have light traveling through air. Light is traveling through air. We know what the wavelength is in air. Okay, we know what the wavelength is up here. Okay, we know what that wavelength is. And then we need to know the index of refraction of, so we're solving for water, so let's say water. Okay. So the wavelength inside of water would be the wavelength inside of the air divided by whatever the index of refraction is. That's how we're going to be using this equation. Okay. What you need to know is that the reason this has all wavelengths in it is because the frequency doesn't change when you transition from one medium to another. So when the light goes from air to water, the frequency is going to stay the same, but the wavelength is going to change. Okay, if you remember the speed of light equation, it's c is equal to wavelength times frequency. So if frequency is staying the same, and wavelength is changing. In order to keep the equation satisfied, that means the speed of the light has to change. Okay, and that's exactly what's happening. When the wavelength changes, the speed of the light is going to change, and it's the difference in speed that what gives us a distortion in an image. Okay, in the world of physics, they call the index of refraction in a vacuum, they have that labeled as 1. So that's the default value. If the index of refraction is 1, then you know we're talking about a vacuum, or in other words, outer space. Okay. If you look at the difference between these two, one is a vacuum and the other one is an air. Notice how the numbers are basically the same. They're both essentially 1, which is why we consider the speed of light in outer space to be the same as the speed of light in air, because there's really not that much difference. But with everything else there is. You can see that water is 1.33, ethyl alcohol 1.36, and the numbers only get higher. Okay. And the numbers of all mediums are always going to be greater than 1. Okay. What that means is that light slows down in everything else besides a vacuum. Light travels slower through everything else. That's what that means for index of refraction to always be greater than 1. Okay. And you have different tables for it. So the greater the number, the slower light travels in that medium. Okay. So this question, the light travels the fastest through what? Okay. So what you will look for is which one of these has the smallest number. The smallest number is vacuum, which is 1. And we know that's we discussed previously. Light travels fastest in outer space. Okay, in a vacuum with nothing to slow it down. Okay. For all transparent material, okay, transparent means we can see through it. The index of refraction is what? Okay, well, we already said that the lowest value is 1. We call a vacuum 1. 1 is the base number. Everything else has to be higher, which means all other materials, it has to be greater than 1. Okay, these questions are just for a reminder. This one we have to do a calculation for. I'm not worried about that. I want to focus more on the concepts. Here, last one. When a light ray enters a medium with a different index of refraction, okay, and we have to see which one of these is true. Its speed and frequency change. That's false. Okay, and we said earlier, frequency never changes. Frequency does not change. Wavelength and speed do. Okay, its speed and wavelength change. Yes, this is the one we know to be true. Its speed does change, wavelength does change. But let's check the other ones. Frequency and wavelength, no. Okay, we already said frequency doesn't change. And then this has all three, and that can't be true. Okay, so speed and wavelength are what change when you transition from one to the other. Okay, what causes this? There's this principle called the principle of least time. I'm not going to bother reading this. You can read it if you like. But the idea is that light wants to take the path of least resistance. Okay. So here we're on the beach and we got a boat. Okay. And let's say you want to travel from the beach to the boat in as short a time as possible. Okay. You're on the beach and you want to get on the boat. The boat isn't going to move. You have to travel to the boat. What is the fastest way for you to get to the boat? They give us a prompt and they tell us we can run a mile in 10 minutes and we can swim a mile in 30 minutes. So the only reason they tell you that is to tell you that you can move faster on land than you can in water. Okay, and that's the case. I believe that's the case for most people, unless you're a fish. Okay, unless you're a human hybrid fish, you're gonna travel faster on land than you will on water. Why is this relevant? It's because they have a straight line drawn from the beach to the boat. Okay, if we're just on paper, this line is the most direct way to get to the boat. Normally, the fastest way to get to something is to run to it directly, right? But in this case, it's not that simple. because we have a transition. We have land here, and we have water here. Once you hit water, you're going to start moving slower. So you have to come up with the fastest way to get to the boat. You have to strategize a little bit. Okay? Okay? You have to strategize a little bit. If you run straight to the boat, you're not gonna make it the fastest because you're gonna spend a lot of time in the water and you go slower in water. Okay, so you might think to, instead of running all the way through it, let me get to this point so that way it's the shortest amount of time in the water as possible. Okay, but that's not perfect either. So there's a Goldilocks, okay? There's too much time in the water, and then you might have gone too far on land. So there's a perfect little medium, and that perfect little medium is what light tries to do. Okay, that's what all this is for, is just to explain that. Okay, light takes the path that minimizes how long it takes to get to whatever object is there. Okay, that's where this index of refraction comes from. Okay, because light bends a certain way, it wants to bend in a manner that gets it to its final destination as quickly as possible. Okay. That's what determines those index of refractions. Okay. So all this last little piece, N1 is air, N2 is the water. The index of refraction is less in air, meaning it goes faster in air and it's greater in the water. And they show you that with the velocities as well. And that results in the light bending, and you get your final path. That's where it comes from. How are we doing on time? Because I don't want it to take too long. Okay, boom. Almost done. And then you have this Snell's equation, which you guys do not have to worry about. Okay, you do not have to worry about that. I've got the main points across. So some quick review. Light traveling at an angle into a medium with a smaller index of refraction is refracted. Okay, and let me make this part clear. Okay, this is towards the normal. Remember when we were talking about forces and we talked about a normal force, or Fn? A normal is just perpendicular to the surface. Okay, so if we call this the surface, this is our surface. This line is perpendicular to the surface, so this is our normal line. Light is traveling this way, but notice how it bends. It bends towards the normal. Okay, so when light travels into a new medium, it is always going to bend towards the normal. That's what they mean when they say that. Okay, so that's what this is. The last thing light can do is disperse. This dispersion is just the separation of light. Okay, light is normally white. You have white light, but that white light is made up of a bunch of different colors. Okay, it's made up of the colors of the rainbow, as you are well aware. But why does it split the way that it does? If light travels in a straight path, you would think that all the colors would overlap. And if all the colors overlap, how the hell do you get a rainbow? How is that even possible? The only reason we can see the colors of the rainbow is because the wavelength of the light affects the index of refraction. The wavelength of the light can change these angles. Okay? It can change these angles. So here they have a little chart. The bottom is the wavelength, and then this is the index of refraction. As wavelength goes up, notice that the index of refraction for most of these goes down. Okay, that's relevant because that means that if you change the wavelength, you're going to get a different amount of bend. Okay, so you're going to get different amounts of bending. So something might be like this, like this, like this, or like this. It might not bend that sharply. It depends on the wavelength. If you remember from the visible light spectrum, every color has a different wavelength and they have different strengths. Red is the weakest, violet is the strongest. And if you remember, the more energy you have, the higher your frequency and the lower your wavelength, okay? So red is going to have the longest wavelength, violet is going to have the shortest wavelength, okay? If you see here, the longer the wavelength, the shorter the index. The shorter the wavelength, the higher the index. Okay? And the higher the index, the greater the bend. Okay? So what that means, if I was to label these, okay, let's say this would be your violet, V for violet, and then this might be your red. Okay? Red is going to bend a little less. Okay? And it's these differences in wavelengths that cause you to see the rainbow. Okay? So when light is traveling through this prism, it's refracted. Okay? It's refracted twice, at the front and at the back, as it says here. But as it's bent, because it's made up of all these different colors of light, every single one is going to bend slightly differently. Okay? Over here, it's in a straight path. Okay, everything is as one, but when it enters, now it has to bend. But because it's made up of different colors, each color is going to bend slightly differently. Some is going to bend more, some is going to bend less. And it's because of that that you get this separation that causes the rainbow. So that's what dispersion is. Dispersion is just separation of light into colors. But the only reason that it happens is because wavelength affects how much it bends. Okay, that's the only reason that happens. And if you spray, on a hot summer day, if you spray water in the air, sometimes you can see the rainbow. The reason you can see that is because the water droplets are behaving like a prism. Okay, the light is going through the water, it's refracting, and then that bend causes you to see the colors. Okay, that's where the rainbow comes from. So again, just to summarize, you have reflection. Reflection is what lets you see images, okay? You have refraction. That's what causes distortion when you go from one medium to another, in this case, air to water. And you have dispersion. Dispersion is just the separation of the different colors of light, okay? That stems from different wavelengths that cause different amount of bending, okay? That's the gist. That's what I want you to get from this. I want to cover one quick thing on reflections. So again, if you have a perfectly smooth surface, you will see your reflection. You'll see an image. Okay, you'll see a perfect image of whatever's in front of it. But if the surface is not smooth, if you have a bumpy surface, then you will get a distorted image. Okay, and that's how they make privacy windows. Okay, a lot of people in their bathrooms, if you have a bathroom window, they'll make that window a privacy window. What I mean by a privacy window is a window that lets light in, but you can't see an image through it. Okay, to protect your privacy. It's in the bathroom. Okay, you don't want people sneaking on you. You're in the bathroom. You don't want people watching you. So they make privacy windows like that. The surface of these are not smooth, okay? So that light bounces everywhere, it scatters, and you don't get a perfect, clear crystal image, okay? Another way you can do it is if they don't want to make the surface rough, they'll put a coating on it, okay? They'll put a coating on it that makes it that it's not transparent, okay? Stuff like this, okay? You see where the top, you can see through the top, but you can't see through the bottom. That's because that piece, whatever they put on it, is not transparent. It doesn't let light through. It's opaque, okay? But that's another thing, okay? If the surface is rough, then the light bounces everywhere and you don't get a crystal clear image. Okay. Okay. So for today, you have just 5 quick multiple choice questions that just I'm making sure that you understand what's going on, and they just quickly summarize what we just went through. Okay. Since there's not that many questions, I don't want to go through one because I'm cutting the work down significantly at that point. But the only mathematical piece is this. 3 is the only one you have to do a math calculation for, and the equation you need is at the top. Okay. Again, the wavelength in the new medium is equal to the wavelength entering divided by the index of that new medium. If you look at number 3, it's telling you you have light in air with a wavelength. So the wavelength is given to you. It's asking you what is the wavelength when it goes in glass, and it gives you the index of the glass. So the wavelength in the new medium is what you're looking for. You know the wavelength entering, and you know the index in the new medium, so you can answer the question. Okay, but that's it for today. I wish you guys the best. I hope you got a good weekend. Happy Monday. Again, if you have any concerns or questions, please feel free to reach out. Take care, guys. Have a go.